Hi, good afternoon, everyone. Welcome to our second event in our designer series. Apologies, this is actually the wrong cover, but we have Julia Keane here to present on psychrometrics, so we're very excited. Just a few housekeeping items before we start. Our next in the series is going to be electrification case studies on March 24th. So if you would like to sign up for that one, please visit our website. All of these upcoming events are listed on our website for sign up. And then in April, we're going to be having applications of radiant heating and cooling systems in buildings. Also coming up, we're very excited. Our March dinner meeting is going to be on environmental control and life support in space. So we are very excited to be having Christina Ciardulo come and speak to us on that. So if you would like to join us either in person or online, please visit our website. Then some upcoming exciting YEA events. We're having an escape room on March 3rd. Please note that we have limited availability for these events, so please sign up as soon as possible if you are interested in either the escape room, or we are having a training series for Mitsubishi will be hosting. So there's only 20 spots for each, so it's on a first come first served basis. And then also, if you are a student member today and you are interested in a scholarship, we're having an information session on March 30th. So please sign up on our website if you are interested in learning more about that. And then also our big upcoming event in May is our Gala Night. We're very excited to be honoring not only this year's awardees, Gina and Al, but also our 2020 awardees, Ed and Matt. So we are excited to be having this great casino night event at Gotham Hall, and we are going to be supporting tunnel to towers and non-traditional employment for women. If you have any questions, please feel free to reach out to us. And if you would like to purchase a ticket, make a donation, or become a sponsor, all of that information is up on our website on our Gala page. All right. We are also hosting a contest to name our newsletter. So all submissions are due by March 1st, and we'll be selecting a winner on March 15th. You will be receiving a gift card to Keane Steakhouse in Manhattan. All right, and we also have our membership battle. If you have information about the battle and potentially becoming a member, please reach out to Chris and Greg at membership@ashraeny@gmail.com. Also, the top 2 spots will receive tickets to this year's gala event. All right. So for this event, questions, you type them in the chat bar. We will be having breaks as Julia is speaking, so that way you guys can ask questions, so that way you don't have to ask them all at the end. If you are interested in PDH credits, a survey will come up when you exit out of the webinar, so please look for that. And then a recording will be available on our YouTube page. If there's any questions, please reach out to us at ashraeny@gmail.com. Especially if you do not receive the survey for the PDH credits. I know sometimes it does. There are problems with spam blockers. All right, and without further ado, I am going to switch this over to Julia. All right, Julia, you should have control.
Excellent. And can you see my screen, Natalie? Let's just confirm.
Yes. If there's any issues for anybody on the in the audience, please just put them in the chat box, and I'll try to help you troubleshoot.
Very good. Well, thank you. And I'm so glad to be here and be able to talk about one of my favorite subjects, which is psychometrics. I am Julia Keane. I am a faculty member at Kansas State University, a professor of architectural engineering and construction science. So we focus on building design, and HVAC is my specialty. I am a professional engineer as well as an ASHRAE fellow, and I have my high performance building design certification from ASHRAE. Besides working at the university in Manhattan, Kansas, 9 months of the year, I also have my own consulting business, which is Keane Designs, and that's what keeps me busy, active, current in the industry, as well as challenges myself beyond what the academic student environment might provide. So that's a little bit about who I am. I've been involved in ASHRAE for a number of years, both at the chapter level and at society level. I've served on many different committees at society and have moved through the ranks to society vice president back a few years ago. And now I am serving on nominating committee as well as a foundation trustee and on a couple of other committees also. So thank you so much for taking your lunch hour and joining me to talk about psychometrics. Now, I'm kind of curious if I can enter the contest to name the newsletter for the $200 gift certificate, because it is to one of my favorite steakhouses, and it's to Keane Steakhouse there in Manhattan, only because it happens to be my last name. So let's talk about psychometrics today. Where are we going? What are we going to try to get through? There we go. We're going to do a very quick review of the basics, because I'm going to suspect that many of you that are joining us today, this is not your first introduction to psychometrics. Then we're going to talk about space conditions. So how do we decide how much load do we have in a space? How do I condition that space? And then we're going to take that to, not only do I need to know what the space conditions and the load for sizing a piece of equipment at peak load, but I also have to understand my part loads in that system selection. We're going to jump into energy recovery and why that is so advantageous and how the psychometric chart can help us in understanding that. And finally, we'll talk just a few slides about condensation, because we're really looking at what is the power of a psychometric chart and how do we use it more effectively. So we're going to start with the basics, because for some people, the psychometric chart is a little intimidating, which I don't blame them, because there's a ton of lines and lots of numbers on there, right? It's sometimes a little hard to understand. So we're going to walk through step by step, what is a psychometric chart and what is it showing us? But psychometrics is really the science that involves the properties of moist air and the process in which the temperature and or water vapor content in the mixture are changed. That's what psychometrics is. And conveniently, we've got all these different equations and tables that have been combined into a single psych chart so that we don't have to flip between pages. We can just use this one device that gives us a graphical representation. Now, there's lots of different psychometric charts that are out there and available to us as design engineers in the industry. I'm going to focus on the ASHRAE psych chart number 1. Now, as I said, manufacturers produce psych charts. You can get digital or electronic psych charts. You can get psych chart apps. You can see psych charts that ASHRAE has a whole number, has many different numbers of psych charts. We're looking at number 1, which means we're at normal temperature. We're also going to be looking, and that normal temperature is looking at a range that takes us from about 30 degrees to 120 degrees. I'm also going to be looking at sea level. So if you're designing for manufacturing or refrigeration units, you're going to want to be using a different psychometric chart. If you are looking at designing at high altitudes, you're going to want a different psychometric chart. So this is what we would see in most sea level applications for human comfort type of design. Now, ASHRAE psych chart looks a little different and is used slightly differently than some of your other psych charts that you might encounter in the industry, but they all will give you the same answer, and they just have slightly different ways in which we transfer information or draw lines on our psychometric chart. But all the elements are the same. So let's begin with those elements of the psychometric chart. What is on this piece of paper? What do all those lines and numbers represent? We're going to be looking at dry bulb, wet bulb, relative humidity, humidity ratio, dew point temperature, specific enthalpy, and specific volume. And what I've shown here is then the common shorthand or abbreviation that we use for each of these topics. So you might see this if you're looking at an equation, for example, in there trying to identify specific volume. It's often an italicized letter V. So we're going to start with dry bulb. Dry bulb is the easiest psychometric property to measure. It takes a basic thermometer to determine our dry bulb. It's the degrees Fahrenheit of our air. And so it is the air temperature that we are going to see it in most of our equations, in most of our applications, because it's really easy to attain. It is also something that you and I are very sensitive to, right? We can talk about dry bulb all day long. We could be talking about the temperature outside. We could be talking about the temperature inside. We could be talking about the temperature in our vehicles. We could be looking at the thermometer in our home. We could be looking at the settings that we're looking at within our vehicles. There's lots of different dry bulb that we encounter every day. And as a result, we've become fairly sensitive to dry bulb values. The dry bulb I've identified here on our psychometric chart as being a vertical line. And those vertical lines range, and so each of the vertical lines are slightly lighter in the way it's represented, but we see these nearly vertical lines representing our dry bulb temperature. The next value we're going to look at is our wet bulb temperature. The wet bulb temperature is labeled here. And we're going to see that we have those, again, sloped lines up and down our psychometric chart that are going to represent our wet bulb values. They are also these smaller dashed lines that are being represented here. So we see our wet bulbs, and they range, again, we see from this highest point on our chart is 90 all the way down to 30 on our chart. The next value we're going to look at is our relative humidity. The relative humidity are the curved lines on our psychometric chart, and they're the ratio between the mass of water vapor present and the maximum mass of water vapor that can be contained at the same dry bulb temperature. And so that can get a little confusing, and I find that people sometimes try to compare relative humidities. And a relative humidity is really distinct to that specific temperature of dry bulb that we're talking about. And so comparing relative humidities is really kind of difficult from that perspective. It also does not have a unit. It is a percentage. So it's the amount of moisture the air is holding compared to the amount of moisture it can hold. So we see these as our curved lines on our psychometric chart. The 10% is identified down here, and then we see each of these curved lines all the way up to 100%. That means that the air is holding as much moisture as it possibly can. That's our saturation line. There can be no more moisture in that airstream. Now, what we can start to establish as we look at this, and as these lines come down our psychometric chart, is that we can establish that cold air can hold less moisture because our relative humidity lines are coming closer and closer together compared to when our air starts to warm up. That becomes pretty obvious to us, I suspect, as we start talking about summer versus winter. And as I talk about relative humidity in those summer months, we might be talking about a 90% relative humidity day, and that's a really hot, damp, moist day, right? But we could talk about 90% relative humidity days in our winter time too, but they don't feel as wet outside because they're not. Our air, when it gets colder, can't hold as much moisture. I should also tell you, we take advantage of this. We take advantage of this when we do cooling because we want to pull moisture out of our air. And how do we do that? We cool the air down. And as I cool the air down, it's going to release moisture as a result, and that is our condensate water, condensate water that we're collecting beneath the coil. So relative humidity is important to us and something that we will use as a reference. Our humidity ratio is the pounds of water per pound of air. It's represented as a W. This is really the amount of moisture content within an airstream. So the humidity ratio is the quantifiable moisture. It's not relative humidity was simply saying how much could the air hold compared to how much is it holding. Our humidity ratio is really saying this is how much moisture you have in your air. Now, on some psychometric charts, you will see this humidity ratio. Instead of talking about as pounds of moisture per pound of air, you will see it referenced instead as grains. And that's simply a conversion factor. 7,000 grains equals 1 pound of water. So as we see it on our psychometric chart, these humidity ratios are horizontal lines. And if you're talking about it in pounds of water per pound of air, they're little teeny tiny numbers, right? 0.012, for example, or 0.020. These are tiny numbers. If you multiply these numbers by 7,000s, they become nice big numbers. They become whole numbers for us, and so we could be talking about a value of 74, for example, or I could be talking about a value of 68. These become much easier if I don't have a calculator to deal with, right? And so as we start transitioning to being able to use these digital tools like our calculators, it is not so important for us to talk about grains. We don't need that necessarily, but you will see both on different, depending on which psych chart you happen to be utilizing. Dew point temperature is also in degrees Fahrenheit. It is the surface temperature at which condensation is going to occur. And it's all about the surrounding air or the ambient air conditions relative to a surface. Dew point temperatures are where our temperature of degrees Fahrenheit dry bulb and our wet bulb conditions come together. So you will see, for example, at 65 and 65, this is going to then be the line that would represent our dew point temperature. And that's important for us to recognize because it is not specifically labeled on this psychometric chart. On other psychometric charts, it will be labeled more clearly for you. The next, and I think I misspoke, is 65 degrees up to where it hits the saturation line, or 60, where it hits the saturation line. So that's what we're looking for, is our dry bulb and our saturation, and it is not dependent on the wet bulb value. Enthalpy, on the other hand, is our BTU per pound of dry air. This is really talking about both that moisture and that temperature, that both of those elements coming together. It's the internal energy and the workflow energy. Enthalpy is listed on the psychometric chart right here. You will find that these lines actually go all the way across the psychometric chart. So this 30 here goes all the way across and matches this 30 down here. The lines that are drawn on your psychometric chart do not match the enthalpy lines. This little portion right here is the slope of the enthalpy line, and then it goes all the way across our psychometric chart. It discontinues through the body of the psychometric chart because we have these other slopes and these other lines in the center of the psychometric chart. So enthalpy sometimes can be a little harder to get at or to read off of our psychometric chart, especially if we're trying to do it on a printed version, because I'd have to have a really long straight edge to determine that enthalpy value. Specific volume is listed and identified all the way at the top here. It is in our cubic feet per pound of dry air. It's our volume per unit mass. So as we look at that, those are the sloped lines. These sloped lines range from this 12.5, and then you're going to see that the increments are going to be on a 0.1 basis as we move up. So here's our 13, here's our 13.5, and again, another value that we can use as we're doing our calculations. So with our psychometric chart, it is a tool. It's a graphic tool or representation of what is happening, and I can read a lot of values off of it. If you are given two pieces of information, a point can typically be plotted on the psychometric chart. Now, there's an exception to that. I can't have a dry bulb value and a humidity ratio because they're both horizontal lines. But any other two pieces of information, I can plot a point on our psych chart. So let's say that we know a room condition, and our room condition may be 75 degrees dry bulb. So I find 75 across the bottom for the dry bulb value and draw a vertical line. And let's say that our room is also 50% relative humidity. So I find my curved relative humidity lines. I draw each of those lines, and I'm going to look for where they intersect. Where those two intersect is now my room condition. This point represents my room at 75 degrees and 50% relative humidity. From this point, then, I can read off lots of other information. I can read the wet bulb value. Again, I'm just simply taking it back to looking at those lines on our psychometric chart and taking that reading. I can draw a horizontal line, and I can read then my humidity ratio. If I go the other direction, I can read then my dew point. I can find my enthalpy, right, for taking a line all the way across our chart. I can also find my specific value. All of this information can be read from this one single point. And just like this one single point, given any of those other two pieces of information, I could have plotted the same point on this chart. Now, I guess it's lots of great information, but I said it's a tool, right? It's a graphic representation. So we've got this point that represents our room. And so if I have a point on my psych chart and I move that point, I'm going to be changing something about the air conditions. I am either going to be moving that point vertically. In that case, I'm going to be changing the moisture in the airstream. So if I move up on the psychometric chart, I'm adding moisture, so I'm humidifying. If I move down for my point, I'm going to be dehumidifying or taking moisture away. That has everything to do with the latent load or the moisture load within the air. A horizontal movement of that point, so if I move the point to the right, what I'm going to have is I'm going to be increasing the temperature. Increasing the temperature means I'm heating that air up. If I move to the left, I'm cooling that air down because we're decreasing that dry bulb. That has everything to do with the sensible conditions of that air. So latent has to do with moisture, sensible has to do with temperature, and our movement on our psychometric chart represents that condition or what we're doing to that particular airstream. So that's a really brief, quick introduction, and I want to stop for a moment and see if there's any questions that I posted. Natalie, have there any questions posted so far that I can entertain related to the very basics of psychometrics?
Not yet. Please type them into the chat if you guys have any questions.
Excellent. Thank you. So I know that's not very tough stuff. Probably most of you have a lot of experience with that. So now we're going to start taking that information and we're going to talk about our space conditions to begin with. So what do we mean when we have space conditions? Well, let's just assume that I have a piece of equipment. Let's just use a standard unit with a delivery air temperature of 55 degrees and 90% relative humidity. And we're going to have this unit, so that's a standard off-the-shelf piece of equipment. Think of it as a rooftop unit or a fan coil unit, or you could think about it as pretty much any basic, inexpensive piece of equipment out there. It's been designed and rated for a delivery temperature of 55, 90%. That's pretty standard. But I want to know what room conditions can be maintained if I have this specific condition of a space. So I have a room that is a 40 by 50 foot classroom. And in this classroom, there is an exterior wall, or it could have more than one exterior wall, but I have an envelope load. It could be from the roof, it could be from the floor, it could be from the walls, as long as I have a load related to those components, and it could also be the windows, I have an envelope load. The envelope load for our example here is 6,500 BTUH. And it's all sensible load. Let's assume there's no moisture coming in through any of those envelope conditions, right? My roof's not leaking. I don't have any leaking around the windows. So our envelope load is all sensible with 6,500 BTUH. Then I have equipment in the space. It can be the lights in the space. It could be computers. It could be projectors. I have different kinds of things that I have in classroom type of applications, but I can calculate this too, right? These are things that we know how to calculate. And so let's say that our equipment load in our lights in our space is 1,700 BTUH. Again, all sensible. Let's assume I don't have a coffee maker that's creating steam or anything like that. That is all going to be a sensible contribution. Well, also in the classroom, I'm going to have some people. And I need to figure out how many people do we have in that space and how much load should we anticipate from those people in this 40 by 50 foot classroom. Well, if I don't know based on our desks or chairs within the space, or the architect or owner can't tell me how many people in their classroom, I can go to some resources to help us come to that conclusion. I can also go to resources that tell me how much heat do people generate on a per person basis. So if I assume that in our classroom, people are going to be seated and doing very light work, right? It all depends on how that space is being used. What kind of classroom are we talking about? But for our example, let's assume that that is an appropriate selection. Then I can find that people are going to contribute a sensible load to the space, a temperature or heat to the space of 245 BTUH per person. Then I can also look at the latent heat contribution. All of us, because we are breathing and because we are processing in sweating, right? Whether you know it or not, we're all putting moisture out simply because we're exhaling on a daily basis, but also because we perspire whether we recognize it or not. That's how we need more water because we're dehydrating as we exist, right? So we're contributing moisture to the space. The moisture concentration is going to be at a rate of, or heat is going to be at a rate of 155 BTUH per person. So we contribute a sensible load and a latent load to any space that we occupy. Now this is on a per person basis, so I need to figure out how many people are in that space. I'm going to go to ASHRAE 62.1 because they have a convenient table that many of us use on a regular basis for determining the number of people in a space. You could also look at your local code. Your local code may dictate the number of people in that space. It's usually not the number based on egress. That's usually many more people than we often put in our spaces. Now that depends on how we use that space and what the likelihood of us getting up to that full occupancy might be, but oftentimes that may be more aggressive than what's necessary. So let's assume that in our classroom space, we're going to have the same number of people as the minimum of code defines, or also found in the ASHRAE 62.1 standard. With this standard then, it tells us default values for occupancy density, and they have a number of people per 1,000 square feet. I'm looking here at a lecture classroom, meaning that the chairs can move around. In a lecture classroom, I have a number of different classrooms listed here, right? I've got classrooms for younger children. I have a lecture hall with fixed seats, but we're going to concentrate on this lecture classroom application. Again, we'd have to know more about our classroom, more details from our owner to be able to come to this conclusion on our own. So I'm simply telling you that for our example, it is a lecture classroom. And with that, it's telling us that we have 65 people per 1,000 square feet. Well, our classroom dimensions is a 40 by 50 space. So I take the area of the room, divide it by 1,000, multiply by 65, and we get 130 people in our space. With that, then, we can now calculate the load associated with the people. The people load, we're going to take that 245 BTUH per person sensible load times 130 people, and we get 31,850 BTUH. Then I'm going to take our 155 BTUH per person times our 130 for the latent load, or the moisture heat that's being contributed, and I get 20,150 BTUH to that space. So now we have the loads for this space, our envelope, our equipment, and our lights, and our people. So we've got all these things that we need to take into account when we're sizing the piece of equipment delivering air at 55 degrees and 90% relative humidity. So to do this then, I need to also talk about the total load. And the total load is simply taking our sensible load plus our latent load. That's going to give us our total load for the space. So I take that 40,050 BTUH, where'd that come from? Well, that was simply our people sensible load of 31,850 plus our envelope load of 6,500 plus our equipment and our lights of 1,700, and we get that 40,050. We have our latent load, and the only latent load is coming from the people, so we've got our 20,150, and I add those two values together, and that's where we get this 60,200 as our total load for the space. This information is important to me because I want to apply what we refer to as a sensible heat ratio. A sensible heat ratio is the sensible load, or that dry heat load, relative to the total load in the space. So I'm going to take how much sensible load do I have over the total load that we've just established, and when I look at that ratio, I'm going to come to a value of 0.665. That value is really establishing for us, of the load we have in the space, how much of it is sensible, right? So our sensible load for our sensible heat ratio is 0.665, and this returns us back to needing to use our psychometric chart. So on our psychometric chart, we have a little graphic over here that we're going to be looking at, and it has a sensible load over the total load, QS over QT. Now, depending on whose psych chart you might be using, they may use a reference point in the center of your psych chart and then have a list of numbers over on the far edge of your psychometric chart for your sensible heat ratio. I've seen a number of different ways in which we can do this. They will all have you drawing a line. Okay, we've got to establish the slope of the line related to our sensible heat ratio. So what I'm going to do is I'm going to take this line and I'm going to have it so that I go from that hatch point in the center of that chart to our 0.665 value that we've just calculated. This now establishes for us a slope of a line. I also know the piece of equipment I want to use. The piece of equipment I want to use is going to deliver air at 55 degrees, 90% relative humidity. So with that, I have my supply air condition that I can plot on my psychometric chart. And I want to establish what condition am I going to be able to maintain within my space. And when I say condition, what temperature and humidity will I have within my space at that load that we just established if I deliver air at 55 degrees, 90% relative humidity. To do that, I plot that 55 degrees, 90%, and I draw then a parallel line. So these two lines are parallel lines. I take this line and the slope we just established and draw it from the center point of our 5590 up in that same angle. So the exact same slope of the line. And this is what we refer to as our sensible heat factor line. This sensible heat factor line is really important to us because that line has now just established, based on the delivery air that you are going to be putting into that space, what conditions we can achieve within that room based on that sensible load and that total load. So let's say that I want to target a temperature of 75 degrees, 50% relative humidity. That's a fairly common value for us to use in our industry. So let's say that we want to have 75 degrees, 50% relative humidity. We can plot that point. When I plot 75 degrees, 50% relative humidity, it falls below the line, that sensible heat factor line we just drew. That means that I can't attain that with that air condition entering into the room. I have to land on the sensible heat factor line for the conditions of the space. I can't be above, I can't be below, I have to land on the line. And because we are below the line, I am not going to be able to maintain a temperature of 75 degrees, 50% relative humidity in this space using this particular unit. It doesn't mean that we shouldn't use the unit. It simply means that I'm not going to have 75 degrees, 50% relative humidity. What I can do, though, is I could have the temperature of 75 degrees, but the relative humidity is now going to be 58 degrees under these conditions. Or I could maintain 50% relative humidity, and in that case, I would have 81 degrees as the temperature in the space. I have one or the other. I can't have both based on the sensible heat factor line and the conditions of the air entering into that room. Now, most people are not very sensitive to humidity. Most of you, if I were to ask you what is the humidity in your space right now, and I asked you the temperature of your space, you'd probably be pretty close at estimating the temperature of your space, but probably a ways off on your relative humidity. That's pretty typical. We haven't been conditioned for our relative humidity. And so what's going to happen is if my space is 58% relative humidity instead of 50% relative humidity, but I'm maintaining a temperature of 75 degrees, it will actually feel a little warmer than 75 degrees because relative humidity is going to influence how we perceive the space. But it is going to be below what we usually identify as the highest relative humidity we want to accept in the space, and that's 60%. We usually don't want to go above that value, because we want to control mold growth, we want to control bacteria growth, those kind of things. And so we typically say below 60% is where we want to be. So we're below the 60%. I expect that most people will not know that they're at 58% versus 50, but they're at 75 degrees. And so this could be an acceptable application if all we're concerned about is human comfort. Now, I know sometimes we have to design systems that are for more than human comfort, for manufacturing, for process type of applications, laboratory applications. In that kind of situation, we may not be able to use this inexpensive piece of equipment that's delivering air at 55 degrees, 90%. I may have to go to a more sophisticated, a more complex, more customizable or modular type of equipment that's more expensive. But for human comfort, 75 degrees, 58% is probably okay. Now, I probably, for a human comfort application, won't take the temperature up to option 2 with 81 degrees and 50%. Probably not such a good option for us. But I think it's really important for us to understand that if we don't land on the line for the conditions that we have established here, we are not going to be able to have that condition. We will not be able to attain that 75, 50% because we're below the line. We have to land on the line. Okay. So let me stop for a second and answer questions because I think a couple may have popped up.
Yes, we actually do have a question. So the question is, why can't the HVAC unit achieve conditions above the line safety margin?
So if we end up above the line, so if the condition, so the air being delivered, we are calling is set. Our unit can deliver 55-degree air at 90% relative humidity, and that's what this unit's capable of doing. That's what it does, okay? In that particular case, if we are above or below that line, we're not going to be able to take care of the sensible versus the latent load in the space. We have essentially said that that slope of that line represents the sensible versus latent load. And so going above or below means we're either not going to take care of the sensible load or we're not going to take care of the latent load with our design approach. So I think that's a great question, and it may become a little clearer as we look at our next example.
Are there any other questions before we move on? Okay. No takers right now, so I think.
All right, perfect. So the next thing then that we need to look at then is how much air do I need to move to the space? If we say that 75-degree air is going to be what our target is, and it's okay for us to have 58% relative humidity, how much air do I actually have to deliver that is at 55 degrees, 90% relative humidity? Well, we go to the equation where our sensible load, our space sensible load, is equal to 1.1 CFM delta T. Now, the 1.1 is a number that will change, and that's so at standard air conditions at so our typical human comfort type of application at sea level, we're going to use a value of 1.1, or you might see somebody use a value of 0.08 or something close to that value. As our altitude increases, this number is going to change. If we are doing more extreme temperatures one way or another, this number would change. But for most of common applications, we see that 1.1. We can solve for our CFM as long as we know the room entering and room leaving conditions. So if my air entering the room from the supply diffuser is 55 degrees and the room temperature leaving the room, so if I set the thermostat at 75 degrees and I assume that there's not going to be a major heat gain within the space before it enters that return, what I'm going to find is that I'm going to have a CFM that is going to be equal to 1,820. That is how much air we need to deliver in order to have our space conditioned at 75 degrees, 58% relative humidity with this sensible and latent load with a unit that is delivering air at 55, 90% relative humidity. Now, one thing that some people sometimes forget is that our CFM is always based on the sensible load. We don't do it on the total load, so we don't use that 60,000 value. We use that 40,050, the sensible load only, because it is about the maintaining temperature within that space, because that's what human comfort is usually most focused on. And if we use total, we will oversize that. The latent load has essentially already been accounted for because we're using a sensible heat ratio and we're using that sensible heat factor line. That latent load has been addressed because of the way that we're using the psychometric chart. All right. So we're not done yet. We have figured out at this point what we can have as a room condition. We know that our room is going to be at that 75 degrees, 58% with that supply air, and we know the supply air volume. But that's not necessarily how big our unit is. That's just how much air is coming into our space. And I need to size the coil in that equipment. And many times with a piece of equipment that is doing both our heating, cooling, and ventilation, I have to incorporate that outside air. So ventilation has to also come into play, and my coil has to be able to handle that capacity. So if I have this classroom with 130 people, how much ventilation do I have to have? Well, we can go back to that 62.1 standard, or you could go to your local codes for, you may use the International Mechanical Code or some other code has been adopted in your jurisdiction. And in that case, we're going to look up how much outside air do we have to introduce. So in the case that I'm looking at 62.1, what I'm going to use is I've got an equation for ventilation, and it's going to take the CFM per person, so 7.5 CFM per person, and we're going to have a CFM per square foot of 0.06. We know the number of people. We already established that as being our 130 people. We know the area of the space is our 40 by 50 classroom. And so I'm going to take that 40 by 50, multiply it by 0.06. I'm going to add to that then our 130 people times 0.75, and I get 1,095 CFM that I need to deliver to the space that is going to be our ventilation air. my coil has to condition that ventilation air, that outside air that I'm bringing into that space. So let's represent that on a psychometric chart. Our delivery air temperature, we know the air that we're going to have within the space, and we have our outside air established. This is what our conditions are for this particular example. Depending on where you are designing will dictate what these outside air conditions are. And there's weather tables that we can get from ASHRAE that will tell us what design conditions we should be using for our design. So let's assume for our location, we say that it's 90 degrees Fahrenheit dry bulb, and we have a design wet bulb that goes with that of 72. So if I know those two conditions of our outside air, I can plot the point, right? I have a dry bulb, I have a wet bulb. With those two, I'm going to plot that point. So I have this representing my outside air condition. So once I know those two pieces, I know that this teal dot, right, that 1095 is going to be associated with the outside air. We know that there's air coming into the space. It's going to be this green dot. But what we also need to recognize is that a portion of the air has to come from the return, right? If I have 1,820 CFM going into the space and 1,095 CFM of that is outside air, then I have return air that's going to be the remainder of that. That return air is simply our 1820 minus 1095, and we get 725 CFM of return air. That return air I know is going to be at 75 degrees dry bulb, and it's going to be at 58% relative humidity. With that, then I can determine the mixed air temperature. When those two air streams mix, my return air is going to combine with the outside air. That's going to be our mixed air coming into the coil. So when those two air streams mix, we know proportionately how much of it is outside air and how much of it is return air. And I can simply draw a line between the outside air and my return air, and I have to land on that line with our mixed air. I can't be above it or below it. If I'm mixing those two air streams together, it always lands on this line. If it's 50-50, we're going to fall in the middle of this line. The more outside air I have, the closer we get to that outside air condition. The less outside air and the more return air, the closer we're going to be on that line to our return air condition. So we're right in this location here. How do I know that? Well, I know I've got 725 CFM of return air, 10,095 CFM of outside air. So I know the temperatures of each of those. I can calculate then what is the mixed air results. Right? I can do the ratios or the percent outside air and establish then my dry bulb condition. With that dry bulb condition, I draw a vertical line till it intersects this mixed air line in between the 2 points that we're mixing, and now I can represent my mixed air condition. So that simply tells us where are the points on the psych chart, right? Graphical tool, it's helping us understand what's happening with those airstreams, but it hasn't answered the question yet of how big does my coil have to be? To answer the question of how big does your coil have to be, or your unit capacity, we use the equation of 4.5 times CFM times delta H. So to do that, let's go back to our psych charts. The CFM we know, our CFM is 1,820 CFM. We know what we have as far as our delta H also. Our delta H is going to be two air streams, right? We are looking for the delta H, or the change that's happening in enthalpy. H represents enthalpy. What is the change that's happening between that mixed air to the air that is being delivered? How much work does my coil have to do? That's really what we're asking. My coil has to take this point and get it to this point. That's what we're asking that coil to do. So to do that, I'm going to take that 33.8 associated for the enthalpy for my mixed air. I'm going to take the enthalpy associated with the air that I need to deliver, and that is my delta H. With that information, then, we can plug it into our equation. 4.5 times our CFM of 1820 times that delta H of 33.8 minus 22.3, and that gives us a value of 94,185 BTUH. I can also talk about this in tons, and it'd be 7.8 tons would be the capacity on that coil. Now, sometimes we don't love using enthalpy. hard to sometimes get off of a chart if we're drawing it, right, with at least with good accuracy. So we could also think about this as sensible and latent load rather than enthalpy. I have to change this point of our mixed air to this point here of our delivery air or my supply air. We've got this change of cooling. So that's the sensible change that has to happen. I've got to get it from 84 degrees down to 55 degrees. And I've got to pull moisture out. I've got to move vertically. I've got to go from my outside air in this location here, and I need to change the amount of moisture down to this line here. And so this is our latent change, or our dehumidification of that air as it comes into the coil. That's what we're talking about when we start talking about condensate coming off of a coil. We're dehumidifying. So I could calculate it using that equation, those two equations also. I could solve for the sensible load on my coil. I'm going to use that 1.1 equation. I'm going to change the delta that I'm using. I'm changing it from my mixed air condition to the coil leaving condition. That's the amount of work that coil has to do. And that gives us our 58,058 BTUH. I could solve for the latent load on the coil. And with the latent load, I'm going to use an equation that's 4840 times our CFM times the delta W, which is our humidity ratio. We pull that off of our psychometric chart, and when we plug that in, we get a value of 35,235. When I add my sensible load plus my latent load, I get a value of 93,293, and that's approximately 7.8 tons. So it doesn't matter if I do it either way, both give us the same answer. Now, these two answers are not identical, right? We can see here that we're about 1,000 BTUH off. That's the accuracy of the psychometric chart. You know, we've got a pencil lead, or we have a line in our PowerPoint, right, width that could be off. Now, if you're doing this digitally, using a digital psychometric chart or an electronic psychometric chart, your answers are going to be much closer, right? They're going to give us much more precise readings, but they're approximately the same. In an HVAC design, the design, quite honestly, is approximated anyhow. But this is how we go through and establish, based on our space load, what we need for our unit load. So I don't notice any questions. So let's look at this graphically. As I look at this, and what I'm going to establish is that I have 4.5 tons of cooling that I need for the space. That's this purple box. This purple box is the air entering, the space conditions. The latent load is this vertical leg, sensible load, but 4.5 tons of load for the space. The load on the coil is 7.8 tons. This is the addition of that outside air that gets us up to 7.8 tons. And sometimes we say, oh, what if I went to 100% outside air? Well, on that really hot day, you're going to have 9.9 tons. And that's why oftentimes we don't go to 100% outside air, but instead use the minimums defined for us by code for ventilation. Now, let me just stop for a second. Natalie, are there any questions before I move on to changing our problem a little bit?
No.
Okay, perfect. So this is great for this classroom. We've figured out how big the unit has to be, but we haven't accounted for that classroom will not always be occupied. That means that at least not with 130 people. There could be far fewer people in that space depending on what day it is and what class it is, right? So what happens when I'm at part load because the class is smaller than the 130 capacity? The envelope, let's assume it's the same outdoor conditions that day and we've got the same equipment operating, but we're going to go down to 30 people in that space instead. With 30 people, we know the sensible load and latent load associated with people will reduce. So the blue numbers are all representing this reduced load. And we will see that we have a total load that is now in the level of 20,200 BTUH. We'll also see that we have less latent load in the space. And as we see less latent load, that means our sensible load increases. And we are seeing a sensible load then for our sensible heat ratio of 0.77. So let's look at what that looks like on a psychometric chart. So this is what we had originally with full load. And at part load, we're going to see that that line flattens, right? We have less sensible compared to our latent load. So our part load sensible heat line factor. We also know that there's likely less outside air that's going to be necessary because I only have 30 people. And if you have demand control ventilation, I'll have the opportunity to bring in less outside air. So I only need 345 CFM in this instance. So we can go through that same exercise, right? We've got then our delivery air conditions. We will find that we will be able to have 75 degrees. Our humidity gets better, right? Instead of being up at 58%, our humidity is going to be controlled at 53%. So that's a better place for us to be from a ratio. And what we're going to also be able to establish then is all those same factors. We can do those exact same calculations because we know there's more return air because there's less outside air. And this is assuming our unit is going to be a constant volume, so still delivering 1,820 CFM. With that, then, we can calculate the load. So exact same equations. All we're doing is modifying things a little bit for our part load conditions. Under our part load conditions, what we will find is that we have changed our delta H. Our delta H now results in a fact that I only need 5.1 tons, or we could do it sensibly and latent wise, right? So we have reduced the amount of cooling that we need when I have only 30 people in the space compared to 130 people. That's not a surprise. We fully expected that. This is great. If I selected an 8-ton piece of equipment, I rounded my 7.8 up to 8 tons, and I only need 5 tons because I have fewer people, then we have plenty of capacity. But wait, you have to stop and think about this. What happens when you provide 8 tons of cooling to a space that only needs 5 tons of cooling? You end up with really cold people in your space, right? So this is a lot of the time. There's most of the time when we do design and we design for our peak, we really have less people most of the time. We have lower outside air temperatures, less solar load, and not all the equipment or lights are on at the same time. So it is very common for us to not need all of that capacity. So what can we do? Well, we could increase our supply air, because if you're going to deliver 1,820 CFM, I don't need 55 degree air. I could have a warmer air temperature delivered to the space, and that's going to allow me to make sure that I have the capacity that I need to match the desired conditions. So that sounds great until we consider the coil performance line. If you deliver air at 67 degrees, what will happen is that the air is coming out, it is going to cool down, and it will only cool to this location here. It will not go all the way down to 55-90. It will cool down to 67 degrees. What you will note then is I've done a lot of sensible cooling, but I've done no latent cooling. We missed this whole portion of the coil performance line. We do not take that air and dehumidify it. And so that's going to remove only sensible load, and you're going to have a moisture problem. You are going to have a very high humidity, and it's going to be problematic for your space. For lots of, it's going to be uncomfortable. It can ruin your finishes. So wood in the space, for example, is going to expand. We're going to see wood paneling, wood floors, all problematic with this solution. Another option is to keep our delta T of 20. So go change that delta T. So it's going to go from 75 degrees down to 55, but I could reduce the amount of air that I deliver to the space. And I could reduce the air using this exact same equation, right? Keeping our delta T, and with our new load capability, I'm going to reduce the airflow to 705 CFM. Now, that can work in certain circumstances. You have to have a fan that can go down to that low CFM. We've got to be able to make sure that we have adequate ventilation still within the space, and we maintain space pressures. Those are all things we've got to be thinking about in that situation. Now, that's not the only, those are solutions, but it's all going to depend on the system type, the application, and the priorities. Another option, when you can't change your air volume, is just impossible for you to adjust the amount of air being delivered. You can reheat the air. That is another option. It is best if we can use waste heat in some way, and it can have the potential to have additional energy use for that fan and the reheat component. But if we look at it psychometrically, what we're doing is we're taking this unit, we're going to cool the air from our mixed air all the way down to 55 degrees, and I'm going to heat it back up to 67 before I deliver it to the space. This pink line represents the reheat function that is happening. That's the amount of heating that you have to do in order to manage the humidity if you're going to stay at that full volume of 1,820 CFM. Another option that we have is that we can use phase and bypass coils. Now, it again depends on the type of equipment that you're using and whether it has this capability. But what it can do then is I can have a portion of the air that gets down to that 55 degrees, a portion of the air that bypasses. We combine those two air temperatures to deliver our 67-degree air. It allows us to dehumidify that air. The mixing of those air streams is where we're going to be landing here. You're going to find that you're not going to fully dehumidify that air, right? It's going to be less dehumidification, but potentially adequate for your application, okay? Another option that you could look at is using multiple units or staged modulating compressors. Again, it's all about the system type, the application, and your priorities in your design. All of these are absolutely options as you're looking at how to handle that part load application. Now, I noticed that I'm 1 minute past 1 o'clock, and I want to be respectful of your time. So I'm going to get through energy recovery, the next few slides pretty quickly, and then at the end, we'll answer some questions. So sometimes you may wonder, why do we use energy recovery? Well, energy recovery is going to allow us to reduce our outside air load. And so if I were looking at this same example, and we said we were at 60% outside air, that's what our 10,095 is compared to our supplier of 1,820, then what kind of impact does it have when I add energy recovery? Energy recovery simply means that when my air is coming in, I'm going to precondition that outside air with air that's leaving the building. I'm going to have a wheel or a plate or some other device that's going to allow us to have this heat, both temperature and latent exchange. Assuming that we have a 50% effectiveness on both our sensible and latent load capabilities, what we're going to be able to do is that we would have, instead of at 90-degree air coming into my coil, I would have 82.5-degree air entering that coil. That 82.5-degree air would be this point right here on our psychometric chart. That is a big difference between 90 degrees when we look at it here. The other thing that we're going to also represent here is now we're going to have a different triangle, that's because I'm going to still be mixing air. I'm going to be simply mixing the air that needs to go into that coil with this point here in our return air. That means that our mixed air condition entering our coil is this black dot. That is going to allow us to have a triangle that is much smaller. It went from that 7.8 tons down to 6.2 tons. And this is a pretty small system, right? We're talking about one classroom. That's a big deal when we start talking about the potential for energy savings. That is 20% energy savings in this application. I'm using only a 50% effectiveness, and that's not a great energy recovery wheel. So just consider energy recovery, and this is what it looks like when we do it on the psychometric chart. Lastly, condensation. Sometimes we wonder, am I going to have condensation on the outside of a supply or a duct if I'm going to be routing 55-degree air through it? Do I need to have insulation? Sometimes that ductwork's exposed or in the gymnasium, and I don't want to have to insulate it because it's ugly or costly. So when can I eliminate that insulation? Well, as long as code says from an energy perspective you can eliminate it, then we have to look at, will we condense on the outside of that duct? And the way that we're going to do that is if I know that the air surrounding that duct is at 75 degrees, 58% relative humidity, I'm going to draw a horizontal line. And where I draw that horizontal line, we're going to look at where it intersects with that saturation line. And we're going to find that it's just below probably 59 for our dew point temperature. And with that, then we know that condensation is likely to form if we find that the air temperature going through the duct or the surface of the duct is less than 55 degrees. Or I'm sorry, if it's less than 59 degrees. With 55-degree air going through that duct with no insulation, you will have condensation form. And that is going to then likely trigger you to insulate that ductwork in one form or another. That got me through my content. I apologize for being a couple of minutes over, but I would love to entertain any and all questions that you might have. Natalie, anything that I can answer?
There is nothing right now, but let's give everybody just a couple minutes, so maybe they're typing something out. I just want to thank Julia for presenting today. This was excellent content, a good review for some of us that might have not seen it for a while, so it was great. Doesn't look like anything yet.
Natalie, you may be able to unmute the participants if they want to just shout out a question if they have it. sometimes typing a question takes a long time.
Does not appear I have that ability to unmute. It doesn't look like there are any questions. If there is something that maybe you don't want to ask on this forum, Julia, is it fine if they reach out to you via your email on the screen right now?
Okay, I'm unmuted, absolutely. My email is listed here. Feel free to reach out to me. I'm also on LinkedIn. I'd be happy to connect with any of you at any time. Ask away with questions. I would be happy to entertain them. But again, I appreciate you taking time from your busy day and from your lunch hour to join us for Psychometrics. And thank you so much to the New York chapter for inviting me. I really do appreciate it.
Thank you. We're very happy to have you. Just as a reminder, if you do need PDH credits, please complete the form when you exit the webinar. And thank you, and we look forward to seeing all of you at our March events.